If torque exceeds 130% for more than 4 seconds, the shredder reverses automatically. Not just to clear the jam, to prevent heat buildup that can start a fire. Depending on material and line design, throughput ranges from 20 to 200 tons per hour. But the blades aren't the engineering challenge. The challenge is keeping 2,000 horsepower under control, while feeding unpredictable material into a machine that can't see what's coming. Today, the systems that decide when to shred, when to reverse, and when to stop. Section 1. Pre-shredding and feeding. Before material enters the shredder, it passes through pre-processing. Hydraulic loaders or conveyor belts feed appliances, scrap metal, and bundled waste into the hopper. Feed rate is the first constraint. Too fast, loss of control. The shredder jams. Too slow, throughput drops below profitability. Conveyors adjust speed based on motor current. If current draw spikes above 110%, the conveyor slows automatically. If it exceeds 120%, the conveyor stops. This is the first control layer. The shredder never sees overload because the feeder prevents it. Some systems use hydraulic rams to push material into the cutting chamber. Cycle time varies with load density. The goal, consistent infeed. Irregular feeding causes torque spikes, accelerated blade wear, and downstream sorting failures. Section 2. Primary shredders. Slow speed torque. Primary shredders are built for torque, not speed. Shaft rotation, 15 to 30 RPM. Motor power, 200 to 2,000 horsepower. Blade material, hardened tool steel, often tipped with tungsten carbide. Slow rotation allows the blades to grip and tear, not cut. This matters because material density varies by a factor of 10 or more. Plastic film, aluminum cans, steel pipes, all in the same feed stream. A single shaft carries 20 to 40 cutting discs. Blade clearance, 1 to 5 millimeters. Tighter clearance means finer output, but higher torque demand and faster wear. Here's what most people never see. Primary shredders monitor torque continuously. At 110% load, the system reduces feed rate. At 120%, the shaft reverses for 2 to 5 seconds. Past 130% for more than 4 seconds, reverse, or the machine becomes a heater. The reverse cycle can repeat 3 to 5 times before full shutdown. Without this logic, a single jam could overheat the motor windings, snap the drive shaft, or ignite trapped material. Torque-based reversal is why industrial shredders run 20 hours a day without constant supervision. The machine appears to use brute force. In reality, it reacts faster than any human operator. Payoff beat 1. This is what a reverse cycle looks like. Torque spikes. The system detects overload. Rotation stops, reverses, clears the obstruction, and resumes, all within seconds. No operator intervention, no downtime, just automated correction. Section 3. Secondary shredders. High-speed cutting. After primary shredding, material moves to secondary shredders. The goal shifts from tearing to sizing. Shaft speed, 300 to 600 RPM. Cutting method, hammer mills, granulators, or high-speed rotary cutters. The chamber includes screens with fixed hole sizes, typically 20 to 80 millimeters. Material circulates until it's small enough to pass through. Larger fragments stay inside and get recut. This is closed-loop sizing. High speed creates heat. Metal-on-metal contact creates sparks. Dust accumulates. Temperature sensors monitor bearings and motor housings. Above 70 degrees Celsius, the system reduces speed. Above 85 degrees Celsius, full shutdown. Some systems inject water mist or inert gas into the cutting chamber. Dust extraction pulls airborne particles into filter units. Fine dust can reach explosive concentrations. A single spark in the wrong conditions triggers deflagration. Secondary shredders are fast, but they operate inside a narrow thermal and atmospheric envelope. Speed without control is ignition risk. Payoff beat 2. This is what thermal shutdown looks like. Heat rises past threshold. The system cuts speed, then halts entirely. No fire, no damage. The machine protects itself before the operator even notices. Section 4. Particle size control. Output size determines downstream recovery. If shredded e-waste is too coarse, copper stays bonded to plastic. Recovery drops. If it's too fine, Dust losses increase and sorting equipment clogs. The target window is tight, single-digit millimeters. Deviation outside this range reduces metal recovery noticeably. What affects particle size? Screen hole diameter, blade sharpness, feed rate, shaft speed, material composition. As blades dull, particles get larger and more irregular. Maintenance is scheduled by tonnage, not calendar time. Blade replacement often happens after hundreds to thousands of tons, depending on material hardness. Some facilities use vision systems to measure particle size distribution in real time. If output drifts outside spec, the system adjusts feed rate or flags for blade inspection. No manual sampling, continuous feedback, payoff beat. 3. This is what particle size drift looks like downstream. On the left, consistent sizing. Sorting efficiency stays high. Metal recovery on target. On the right, oversized fragments. Copper still bonded to plastic. Recovery drops, value lost. The shredder sets the ceiling for the entire line. Section 5. Over torque and jam detection. Jams are inevitable. A steel rod between blades, wire wrapped around the shaft, concrete too dense to shear. The shredder can't see what's inside. It can only measure resistance. Torque sensors measure rotational force at shaft or motor. Vibration sensors detect imbalance from uneven loading or blade damage. Acoustic sensors listen for abnormal grinding. Temperature sensors track bearing and motor heat. All data feeds into a PLC, Programmable Logic Controller. Response time, milliseconds. Torque spike detected, reduce feed rate. Spike continues, reverse rotation. Spike persists, full stop. Operator alert. Current limiters cap motor draw to prevent thermal damage during sustained jams. The shredder looks like a brute force machine. It runs on continuous measurement and automated correction. Section 6. Downstream sorting. Shredding is preparation, not the end. After size reduction, material moves to sorting. Magnetic separators pull ferrous metals. Eddy current separators eject aluminum, copper, brass. Air classifiers separate light fractions, film, foam, paper. Optical sorters use NIR sensors to identify material type. Air jets divert. Each stage depends on consistent input size. Variation in particle size means variation in recovery. Shredder control determines sorting efficiency. Material that meets spec flows through. Material that doesn't creates bottlenecks, contamination, and lost value. Outro. From 500 kilogram appliances to palm-sized fragments. From 2,000 horsepower motors to millisecond torque reversals. Industrial shredders reduce, size, and prepare material for recovery. The blades are visible. The control logic is not. Feed rate limits. Torque thresholds. Temperature monitoring. Automated jam response. Every ton processed depends on systems no visitor ever sees. If you want to see how shredded e-waste gets separated into copper, aluminum, and plastic, or how battery recycling handles thermal runaway risk, drop a comment. The process after this one is just as precise.